So in today's notes, we're going to be talking about what's called differentiability. What differentiability means is, where does the derivative exist? We've been learning how to take the derivative using limits, but since a derivative is a limit, we can look at one-sided derivatives. And since sometimes limits don't exist, that means that sometimes the derivative will not exist. So let's look at an example. The right-hand derivative at a point A is the limit as x approaches a from the right of f of x minus f of a all over x minus a. Basically what you're doing here is you're looking at the slope close to a number, but on the right side. So if we make a note about this graph, if we look at the limit as x approaches, let's use the number -2 here, from the right side of this formula. What this is really asking me to do, I suppose I should have changed this to a -2, huh? What this is really asking me to do is to look at the slope of this graph slightly to the right of that point. If I draw in the tangent line there, I'm going to notice that this slope is a negative slope. I know that we don't know the exact number here. That's not really super important for our purposes. Now the left side derivative, the left-hand derivative, would be the limit as x approaches a from the left of f of x minus f of a all over x minus a. So if we look at this idea on that same graph, we would have the limit as x approaches -2 from the left of f of x minus f of -2 all over x plus 2, changing it to a plus because it's a minus. If I draw in the tangent line, because it's a straight line, the slope is just going to be this positive slope, this same one. What's important to realize here is that these numbers are not the same. It doesn't really matter what they are, but one is positive and one is negative, so they're definitely not the same. Because a derivative is a limit, and we learned that if you check both sides of a limit and it doesn't match, then the limit does not exist. In a case like this, where the left side derivative and the right side derivative don't match, the derivative would not exist. So what we say is that a derivative will exist if and only if the limit as x approaches a from the left of f of x minus f of a all over x minus a is equal to the limit as x approaches a from the right of f of x minus f of a all over x minus a. In other words, they will only exist if the slope on the left and the slope on the right are equal to each other. They must be equal. Because of that, there are some very specific cases and instances that we can check for to determine whether a derivative will or will not exist. So in the next couple pages of notes, we're going to look at some of these cases. The first situation I want you to watch for when a derivative will not exist is what's called a sharp corner. On a graph, you're going to look for a point like this one, where there's a sharp corner in the graph. That part's easy, just kind of look for it. But if you have an equation, what you need to look for is anytime you have an absolute value function. If you have an absolute value function, it will always have a sharp corner. Therefore, there will always be at least one place where the derivative does not exist. And that place is at the corner. So if we look at this example, it says find all of the points in the domain of this function where f is not differentiable. F is not differentiable means that the derivative does not exist. Because this is an absolute value function and it's got some shifting going on, we need to kind of understand what's going on here. This minus 2 means that we were shifted right 2 spaces. And this plus 3 means that we were moved up 2 spaces. I'm sorry, 3 spaces. So where would this derivative not exist? Normally, the corner is at 0, 0. But we were moved right 2 up 3. So the corner would be located at the point 2, 3, which means this is the place where the derivative does not exist. You could also say that the derivative does not exist at x equals 2. There are going to be some problems where you can't really find the y value, it's not specified enough. So in that case, you would just say that the derivative does not exist at that specific x value. Okay, that's the first situation. That one's called a corner. The second type of situation where a derivative would not exist is at any kind of discontinuity. Now in the previous chapter we talked about that there are types here. There's removable, infinite, jump, and oscillating. In this particular picture, there's a jump discontinuity. But no matter what, if you're ever not continuous, you cannot have a derivative. So watch for discontinuities when you have a rational function. Well, when you have a piecewise function, let's start with that. When you have a piecewise function or a function that might have a vertical asymptote. So watch for denominators. Here are 2 examples. So let's look at, visually you can kind of see discontinuities pretty easily. When you have an equation, how are you going to identify them? I've got a piecewise function here. So my immediate thought is that maybe there's a jump, maybe there's a hole, maybe something weird is happening. So I'm going to check to see if it's connected. If I look at plugging in 3 to the top, I get 1. And if I plug in x equals 3 to the bottom, I get 12. Since these y values don't match, there's going to be a jump in the graph somewhere. There's going to be an open circle and there's going to be a jump. Therefore, we are not differentiable at x equals 3. Now, I'm not really worried too much about anything else. I'm not worried about any other x value. And the only reason I chose 3 was because 3 is the number here where the different pieces split up. Next, the second option where there might be a discontinuity of some kind is when there's a fraction. So if I factor this denominator, I would get x minus 3 times x plus 1. Because there are going to be vertical asymptotes at 3 and -1, that is an infinite discontinuity. So we would say that we are not differentiable at x equals 3 or -1. On the next page, we have two more types of situations where you might have a derivative that doesn't exist. The first type of situation is what's called a cusp. The second situation is what's called a vertical tangent. So let's look at a cusp. Visually, what's happening here is that if I draw it really dramatically, these are angling down towards negative infinity on both sides. Now the graph actually is connected there, but the slope is so steep that the slope would be infinity. It would be vertical. And a vertical line's slope does not exist. In this picture, where it's called a vertical tangent, if you draw in the tangent line right here, where the graph kind of goes straight up and down, the tangent line would be vertical. And for a vertical line, the slope does not exist. Since a derivative is just a slope, those would both have derivatives that do not exist. Now, how are you going to recognize this if I give you an equation? Anytime you have a function with a rational exponent, that means the exponent is a fraction. It's going to have one of these things happen. It's either a vertical tangent or a cusp, and it doesn't really matter which one. Therefore, there will always be one place where the derivative does not exist on that graph. So find all the points in this domain where f is not differentiable. If I picture the graph of x to the 1/3 power, it looks like this. This vertical tangent right here occurs at x equals 0. So I would say that I am not differentiable at x equals 0. This is another reason why knowing what these graphs look like is so important, and knowing your basic parent functions is so important. So let's take a look at some examples. The first type of question or problem I could actually give you and ask you to do is to look at this picture and tell me where the derivative does not exist. Then tell me why it doesn't exist at that value. So there are two steps here. Where the derivative does not exist, explain why. When I say explain why, all you have to say is either corner, cusp, vertical tangent, or discontinuity. So let's take a look. If I go from left to right and just sort of read my way across the graph, the first place the derivative does not exist is at x equals -2. The reason is because there's a discontinuity. The graph is not even connected there. The second place the derivative would not exist is at this cusp. You'll notice the slope gets really steep and goes up, gets really steep and goes up. So we would say at x equals -1 because there's a cusp. We would say at x equals 0, the derivative does not exist because there's a vertical tangent. And we would say that at x equals 2, the derivative does not exist because, again, there is a discontinuity. And this one actually also has a corner. So you could say both or either one, doesn't really matter. You just have to know it doesn't exist there. Now at this problem, it's a little bit different. I'm saying determine whether your function is differentiable at these specific numbers and explain why not if necessary. So this time I'm not saying like just find all the discontinuities. I'm saying tell me yes or no and why. So if we look at -2, this is the same graph as before. We would say not differentiable because there's a discontinuity. But if we look at -1, we would say not differentiable because there's a cusp. If we look at 0, we would say not differentiable because there's a vertical tangent. Now here's what throws people off. A lot of times when the question is phrased this way, if we look at 1, we would say yes, it is differentiable. There's nothing weird going on there. If we look at 2, we would say no, because there's a discontinuity and a corner. And if we look at 3, again, this is what always throws people off. There's nothing weird going on there. So we would just say yes. Now the reason we use the same graph in both of these is I want to show you what the different types of directions are really asking you. So if they say, tell me where it would not exist, I'm only worried about the parts of the graph where something weird is happening. If it says, for these specific numbers, tell me what's happening, then if something weird is not happening, I just say, hey, it's cool, I'm differentiable. Last but not least, if I give you an equation, can you tell me from this equation why there is no derivative? So this one says show. When the directions say show, that means kind of like prove. You have to show the work to convince me that this is true. But you're starting with the assumption that it's true. Like what I'm about to tell you isn't false. It's just you have to show me why it's true. Show that the following function has a left-hand derivative and a right-hand derivative, but there is no derivative there. So what we have to do is we have to find the left-hand derivative first. Then we're going to find the right-hand derivative second. Then we're going to show that they're not equal. So let's work on the left-hand derivative. We're talking about specifically when x is 0. So if I look at this piecewise function, this top function controls the left side of 0. So first, I'm going to find the limit as x approaches 0 from the left of f of x minus f of 0 all over x minus 0. Now in this problem, because the top function controls the left side, I would say x squared minus f of 0 means take an x that's 0 and plug it in, I get 0, all over x, because x minus 0 is just x. So I would have the limit as x approaches 0 from the left of x squared divided by x. One of the x's cancels, so I would have the limit as x approaches 0 from the left of just x. Now I can plug the 0 in and I get 0. So the slope of this graph to the left of 0 is 0. Next, I'm going to find the right side derivative. So I'm going to look at the limit as x approaches 0 from the right of f of x minus f of 0 all over x minus 0. In this problem, the bottom function controls the right side. So I'm going to have the limit as x approaches 0 from the right of 2x minus, if I plug 0 into there, I get 0, all over x, which means I get the limit as x approaches 0 from the right of, if the x's cancel, because the 0 doesn't really matter, I just get 2. So the value here would be 2. Now you'll notice that these numbers are not the same. So the third thing I need to say is that the derivative does not exist because the limit as x approaches 0 from the left of f of x minus f of 0 all over x minus 0 does not equal the limit as x approaches 0 from the right of f of x minus f of 0 all over x minus 0. Even though the left side derivative exists on its own and the right side derivative exists on its own, the overall derivative here does not exist. Now, how can we extend that into answering sort of a question? This was just a prove question, like I'm telling you it's true, tell me that it's true. Congratulations. But on problem number 2, it's determine whether or not we are differentiable at x equals 1. So now the question is, are we differentiable or are we not? The reason we're worried about x equals 1 is that's where the function breaks apart. So it's got a separate part of the function controlling the left side and a separate part controlling the right side. Let's go ahead and use this same work or sort of a similar method to solve this problem. So this is controlling the left side. First, let's look at the limit as x approaches 1 from the left of f of x minus f of 1 all over x minus 1. In this problem, the left side is controlled by x squared. So we have x squared minus, if you plug in 1, you get 1, over x minus 1. We're going to factor. So the limit as x approaches 1 from the left of x plus 1 times x minus 1, all over x minus 1. So we get the limit as x approaches 1 from the left of x plus 1. Now I can plug it in and I get 2. Now let's look at the right side. The limit as x approaches 1 from the right of f of x minus f of 1 all over x minus 1, which means we get the limit as x approaches 1 from the right of 2x minus, if you plug in 1, you get 2, all over x minus 1. Again, I'm going to factor. These cancel. So we get the limit as x approaches 1 from the right of 2. There's really no place to plug it in, so the answer is just 2. This time, these numbers do match. So we would answer the question by saying the derivative does exist at x equals 1. I hope this makes sense. I will see you guys tomorrow and we will practice this in class.